Chapter 2.5, Day 1, Zeros of Polynomial Functions. We're going to use the fundamental theorem of algebra to determine the numbers of zeros of polynomial functions. We're going to find rational zeros of polynomial functions and find complex zeros using conjugate pairs. So the fundamental theorem of algebra states that in the complex number system, every nth degree polynomial function has precisely n zeros. So if f of x is a polynomial degree n, where n is greater than 0, then f has at least one zero in the complex number system. So we're going to determine the number of zeros of each polynomial function. So in the homework, what it's going to ask you for is just how many zeros is possible. So let's just do that real quick. So in this first example, we have f of x equals x minus 2. Since the degree is 1, then therefore this is 1 0. Then letter B, it's a degree of 2, so there's 2 zeros. And letter C, there are 3 zeros. So, but I do want to try and solve for that. So what you do in order to find the zeros is you have to set f of x equal to 0. So 0 equals x minus 2, or x equals 2. Then x squared minus 6x plus 9, that factors to x minus 3 times x minus 3. So we have x equals 3 and x equals 3. It is a repeated 0, but it's still 2 zeros. Then the last one, 0 equals, let's factor out an x. We have x squared plus 4. And so we have x times x plus 2i times x minus 2i. And so here we have 3 zeros. We have x equals 0, x equals negative 2i, and x equals positive 2i. So go ahead and try this example at the bottom, determine the number of zeros, and then just for practice, go ahead and find the zeros. Pause the video, and when you come back, I'll have the answer for you. So if you tried this out, you would see that there are 4 zeros, and so we see that even though they are imaginary, it is still a 0. So the rational zero test. The rational zero test relates the possible zeros of a polynomial having integer coefficients to the leading coefficient and to the constant term of the polynomial. So if the polynomial f of x here, this polynomial, has integer coefficients, then every rational zero of f has the form p over q, where p and q have no common factors other than 1. P is a factor of the constant term, or the back, and Q is a factor of the leading term, the front. So one way that I like to think about this is instead of P over Q, I call it B over F, because I know B comes first and then F. So that helps me in remembering what goes on top and what goes in the denominator. To use a rational zero test, you need to first list all the rational numbers whose numerators are factors of the constant term and whose denominators are factors of the leading coefficient. And so you see that here. Factors of the constant term over factors of the leading coefficient. Having found the list of possible rational zeros, you just have to use trial and error to determine which, if any, are actual zeros of the polynomial. Note that when the leading coefficient is 1, the possible rational zeros are just simply the factors of the constant term. Let's try the example here. Find if possible the rational zeros of f of x equals x cubed plus x plus 1. So we know the possible zeros we have, possible roots, is just positive 1 and negative 1. So let's go ahead and try it out using synthetic division. So am I missing anything? 3, yes, I'm missing an x squared. So 1, 0, 1, and 1. So 1 times 1 is 1, 1, 1, 2, 2, and 3. So that is not a possible root because it has to equal 0 in the remainder. So let's try negative 1 and see what happens. So 1, 0, 1, 1, we get 1, negative 1, negative 1, positive 1, 2, negative 2, and then a negative 1. So what this tells us is this has no rational zeros. No rational zeros. Okay, so I want you to try out this example here. Find if possible the rational zeros of x cubed plus 2x squared plus 6x minus 4. First, you need to list the possible roots by doing b over f. In this case, it's just the constant. So possible roots, and then go ahead and try them out and see what you get. So if you tried this out, you would notice that none of them work, so we have no rational zeros. So let's try this example. Rational zero test with the leading coefficient of 1. Find the rational zeros of x to the fourth minus x cubed plus x squared minus 3x minus 6. So this one will work. And so we just need to list the possible zeros. And our possible zeros are going to be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So we just have to do trial and error. Let's go ahead. Let me try -1. So -1, 4, 3, 2, 1, 0. I'm not missing any terms. So 1, -1, 1, -3, and -6. So 1, -1, -2, positive 2, 3, -3, -6, positive 6, and 0. Wonderful. So that worked. So I know that one of them is x plus 1 is one of my factors. So I'm going to do it again. And so my last number is 6, so I can use the same numbers that I did before. So let me go ahead and try 2 here. So repeated synthetic division. 2 times 1 is 2. This is 0. 2 times 0 is 0. 3 times 2 is 6. And that actually works. So another solution here is x minus 2. And so let's write this. So we know this is x to the 0, x to the first, and x squared. It doesn't always work out that way, that it's the first one. Usually you have to try a couple and then it works. So, but just for time purposes, this kind of helps out. So x plus 1 times x minus 2, and then this is x squared plus 3. So this we know is not a rational zero. So we don't have to list this one. The only one we're listing are the rational zeros. So we know that x equals -1 and x equals 2. Okay, so go ahead and try this example here. Find the rational zeros of x cubed minus 15x squared plus 75x minus 125. And so go ahead and try it out. Pause the video, and when you come back, I'll have the answer for you. So if you tried it out, I tried 1 first, and that didn't work. So I tried 5 and positive 5, and so that did work. So you know to stop when you know that this is factorable. If you can factor it at that end, then you can stop. So I wrote x squared minus 10x plus 25, and that factored to x minus 5 times x minus 5. So this is an odd multiplicity, right? And so that would pass through. And so we just have one root at 5. I hope this helps. Thanks for watching.